Hi and welcome back. This is exciting. You're to the, I think this is the fourth or fifth video of the mini-series, and we're finally going to prove that e is equal to this limit, which is pretty cool. Now to start this proof, you need to have some useful information, and we actually need to start, let me grab my ink, with a function. So the function we're going to start with is f of x equals the natural log of x. You need that function's derivative, which we've already done. We know that's 1 over x. And you need the function evaluated at 1, and you need the function's derivative evaluated at 1. And these two things equal the natural log of 1, which is 0, and 1 over 1, which is 1. This is useful information we're going to use in our proof. Alright, now to start this proof, we're going to use this function, and we're going to also use the limit definition of derivative. And if you recall, the limit definition is f prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. And what we're going to do is we're going to take our natural log of x and we're going to use this limit definition of derivative to see what we get, and we're going to tweak it a little bit. So f of a plus h is going to equal the natural log of a plus h. F of a is going to equal the natural log of a. So when I do this piece, I've got f prime of a equals the limit as h approaches 0 of all of that. All right, now we're going to do a few switcheroos. We're going to let a equal 1, that's our x value, and we're also going to let h equal x. So that's the x value that we are going toward, or that we're going to have substituted in here. So we've got f prime of 1 is equal to the limit, and now we're going to have as x goes to 0 of the natural log of 1 plus x minus the natural log of 1 all over x. Okay, now the next thing we're going to do is we're going to let this equal 0, and we're also going to rewrite this a little bit. Now remember, the natural log is a function, and the limit is very flexible. The limit can kind of sneak into functions because that limit is affecting the piece here with the x. So we're going to rewrite this a little bit, and we're going to call this x in the denominator. We're going to call 1 over x. We're going to put this limit kind of inside here, inside the natural log function. So we're going to say the natural log of the limit as x approaches 0 of 1 plus x. And according to the laws of limits, you are allowed to do that. You can do that. You can take the limit of the piece inside of the natural log. And then using the rules of natural logs, we can rewrite this as an exponent on the thing we're taking the natural log of. So we get f prime of 1 equals the natural log of the limit as x approaches 0 of all of that. All right, let's go to another slide so we can kind of clean things up. All right, now remember from our useful information, f prime of 1 equals 1. So I'm going to rewrite that as 1, and then 1 is equal to all this stuff up here. Now, this is a natural log, and the base here is e. We don't write that there because the natural log indicates that. We can rewrite this in exponential form. So let's go ahead and do that. We're going to have e to the first power equals all of this stuff right here. Now, if you look at some definitions of e, this will be it. This will be the definition of e. But that's not the definition of e that we want. Our definition of e, we've got n going to infinity. So we need to somehow change all of these x's into n's. And if you look at the original thing that we were trying to prove, and I'll write it down here so that we can remember, we've got e equals the limit as n goes to infinity of all of this. So we need to somehow rewrite this. And if you look up here, this is a little clue. 1 over x is going to be the same as n. So let's use that. If 1 over x is the same as n, that means that x is going to be 1 over n if you solve this for x. All right, and then we also have to look at this. Somehow how we have to change this x going to 0 as n going to infinity. So let's think about this for a second. If x is going to 0, 1 over x is going to be the same as the reciprocal of this, which is going to be, if it's 0 over 1, you're going to have 1 over 0. And 1 over x is the same as n. And if you think in terms of limits, as the denominator gets infinitely close to 0, 1 divided by something infinitely small is going to go to either positive or negative infinity. So let's assume that's going to be a positive infinity here, and we get n going to infinity. So if we rewrite this, we've got e is equal to the limit, and then our x changed into n, and when that changes into an n, the 0 changes into its reciprocal, which in terms of calculus is going to be an infinity. And then we've got 1 plus, and the x turns into 1 over n from what we deduced over here, and the 1 over x turns into n. And we've got it. So these two things are basically equivalent, all right? And you will see both of them as definitions of E. This is the one you often see most often, especially in calculus books. And this is the one that you're going to use most often when you get to sequences and series. I hope you enjoyed this series of videos. Keep watching.